So our next speaker is Samarpita Ray, she will be talking about cohomology of modules over H categories and co-H categories. Take it away.
Okay, so thank you for giving me the opportunity to present my work at this conference. So I'm going to talk about cohomology of certain classes of modules over some Hopf categories and some Hopf co-module categories. And so I will start with some, first some background. One of the most important tool that we use to compute this cohomologies is the grothantic spectral sequence. So I will start by recalling first what is a grothantic spectral sequence, and then I want to so basically we use this method of categorification, which is proposed, which was like the celebrated picture of B. Michel, who proposed a method of categorification, which is called the ring with several objects viewpoint. And I will recall that, and then I will be ready to define H category and co-H category and the modules that I'm interested in and the cohomology then. Okay, so let's start first by what is a grothantic spectral sequence. So just to recall, if you have 3 abelian categories, A, B, and C, such that A and B have enough injectives, and you have 2 functors, both additive and left exact functors from A to B and B to C, such that F sends injective objects to G acyclic objects. Then we have a spectral sequence which can compute the higher derived Hopf functors of the composition of the two the 2 functors, the composition of the 2 functors, given that you know the higher derived of each each of the functors. So that's the usefulness of this, that if you can have any functor, you can break it up into 2 parts, like a composition. Then if you know the derived Hopf for each, then you know it for. So that's a grothantic spectral sequence. Now, as I said, I will recall the categorification technique, which was introduced by B. Michel. So it starts with the idea that if you have a ring, it is nothing but a pre-additive category with a single object. If you remove pre-additive, it is just a monoid. So from this light, one can think of a pre-additive category as if it's a ring with several objects. Of course, this word doesn't literally make sense, ring with several objects, but it's the idea which is important, which tells one that one should study ring theoretic properties for categories and some general like basic categorifications, like ring replaced by a pre-additive category. If you have a K algebra, then the replacement is a K-linear category, which is like the Hopf sets should be vector spaces. And modules over a ring are basically functors over a category. This is some standard. And now, as I need some concepts, categorified concepts, I will define it when needed. So this is like the idea. Okay, so we are now set to define what is H category and co-H category. So now let me recall these Hopf algebraic concepts, which is H module algebra and H co-module algebra. So when I say an H module algebra, an H module algebra it's an algebra, which is also a Hopf module, such that the action of the H is very well behaved with there's a compatibility condition with the algebra product. Similarly, an H co-module algebra will be an algebra which is also an H co-module, and the coaction of the H is compatible with the algebra product. From now, the H category and co-H category will be correspondingly the categorifications of these 2 concepts, H module algebra and H co-module algebra. You can also think of an H category as just a category enriched in H modules, and co-H category as a category enriched in the monoidal category of co-modules, H co-modules. So that's the idea. I didn't make the big explicit definition, which will be kind of too much. Okay, so some examples. So some examples are like if you start with any H module algebra, then all the H equivariant right modules, and that forms an H category. Also, if you take the subcategory of that category, which is the finitely generated free right modules, they also forms the H category. Now, this is examples for H categories. And now there's a result that we proved is that if you have a finite dimension Hopf algebra, then any category D is a co-H category if and only if the D is like a left H star, the dual H star category. So this result immediately gives you plenty of examples for co-H categories because it's just the dual that you have to consider. Okay, so these kind of categories, H categories and co-H categories, and the theories over them has been studied by various authors. First, these were considered by Sybils and Solotter, then works by Kenapel and Barista, I think, and Solotter again, and Guedanan, these people, they worked on it. And Guedanan and Kenapel particularly studied the cohomology theory of this, like the modules over the module categories over these kind of categories. In this work, I mean, for the case of algebras, what I wanted to say is that cohomology theory was studied on the level of algebras, like H module algebras and H co-module algebras. And what we do in this is we do the categorification of generalization of these results. Okay, so so now I want to talk about H equivariant modules. This is one kind of the by H equivariant modules, I mean the modules that I'm going to consider on these H categories. So from the perspective algebra, like on the base case, if you consider a half module algebra, the classical definition of an H equivariant module is it's a module which is also an H module with some compatibility. So now the categorified version. So you have, so as I said, in case of category theory, I mean, in the sense of categories, the notion of module is replaced by a functor. So we have the, this is a notion of a functor. So you consider a functor over the category. And the definition is that the H equivariant modules of the category C, where C is the H category, and these H equivariant modules are basically C modules, which such that for each object X in the category, Mx is endowed with the H module structure, which is compatible with the morphisms, like the in the following way. Yes. And by morphisms between these H equivariant modules, what we mean is modules just on the level of category C, category C, such that on the level of each X, because each X, Mx has a H co-module structure, so it should satisfy the H linearity condition. Excuse me. Just excuse me for a second. Shit. Yeah. So we denote this okay. Sorry for this problem. Yeah, so we consider this category, we denoted the H equivariant modules as, we denoted it by this. Now so now we want to say that this kind of modules, the H equivariant modules, the first thing we proved that these modules are basically equivalent to modules over the smash extension of the category. By smash extension, I mean it's a k-linear category, which like it's the objects, I mean, if you have a H category, that the SMASH extension is basically a K-linear category, and the in the new category, or the objects are still same, the morphisms changes. The morphisms are now given by tensor product with the H, by tensor product over K, like the field, and and the composition of these elements are defined in this way. So this is the SMASH extension of the category C. And the first result is that these H equivariant modules that I talked about, they're equivalent to this category of modules over the SMASH extension. This is an important result because this immediately tells us that the equivariant modules is a Grothendieck category, because any module category is a Grothendieck category. And that also helps us to know that it has enough injectives, which we need for the resolution and eventually for getting the spectral sequence. So now I think I am in the place to give the first spectral sequence, which is so given an H module, just a half module, by the definition for the H invariance of the module M are all these elements which satisfies this condition, where E denotes the epsilon of the half algebra. And okay, so now the first thing is that if you're given by C hash H modules, what I mean are H equivariant modules, because we know they are the same thing. And now first thing that we prove is that the modules, the Hom sets, are going to have a H module structure, and that by the morphisms in this category of H equivariant modules are nothing but the H invariants of the morphisms in the base category C. And on the level of derived Hom functors, these leads to the following spectral sequence. That is, we can compute the higher derived Hom in the category of H equivariant modules by knowing the X, which is the Hom in the base category, and the functor, which is the invariant functor. And that gives us the first spectral sequence to compute the cohomology in this category. Okay, so the H locally finite, now I want to talk about a subcategory of this module category, which is also important in the sense that it helps to know, it's like a locally finite subcategory that I want to talk about, and the cohomology of it, because that category is important in the sense that it helps to compute or helps to understand this module category, the bigger category, in different ways, like co-simplicity, etc., or the projective elements. So so that category is like, so for that we need this notion of finite on the level of each element, that is a locally finite category, which is given an H module, we call any element in that module as finite, I mean H finite, if HM is finite dimensional as a vector space. And also the collections of all such elements of M, it is a submodule, H submodule of M. And given that C is a left H category, by a locally finite H locally finite category, we mean it's the category, the Hom sets should satisfy this condition that the H finite elements of the morphisms should be equal to the morphism itself. So this is a H locally finite category, and and by small mod, which I said is a subcategory of the module category, original module category, it is the collection of all these H locally finite modules. And okay, I think I can skip this part where so there is a notion of finitely generated object over modules, just the way we have notion of modules over ring, and you can talk about finitely generated object, like what we can talk about like a module over a ring, which is like finitely generated. In a similar spirit, one can define a finitely generated object in this category, in a category. So that's the idea of a finitely generated object. And having said that, yes. So now the way we compute the the cohomology of this in the smaller category, which is the H equivariant modules, is that, not the H equivariant modules, but the H finite elements, is that first we prove that if you take modules from here, then the Hom sets are going to have a H module structure, because then we can take the invariance, and that will help us to compute the derived category, the derived functors in this smaller subcategory of module category. But the only restriction on this is that C should be H locally finite category, which is a right Noetherian category, H locally finite category. And with suitable M, which is finitely generated module, we can always compute the cohomology in these categories by using the cohomology in the base category and by taking the invariance. Okay, so far I've talked about modules over H categories, and in the last part I will talk about modules over the co-H categories, which is a relative of modules. So in the sense of classical Hopf algebra, an H comodule algebra, or relative modules over H comodule algebra is basically, it's a module, which is also H comodule and with some compatibility condition. So we introduced the notion of categorified relative of modules, which should be that if you have a D module with each object on the level of each object X, Mx should be endowed with the coaction of H in a suitable way. And the morphisms will be the morphisms in the original category, which satisfies the H collinearity property. And such a category will be denoted by D mu H. And first thing, we prove that it's a Grothendieck category so that we know if there are enough injectives. So now if you have any comodule over H, then the tensor product with a relative of module is also going to give you an element in the D mu H. Now, and if you so you have a functor from comod H to the relative Hopf category. Now, because comod H is a Grothendieck category, and this tensor product is going to preserve co-limit, by a classical result of Kashiwara and Shapira, we know there exists a right adjoint, and that right adjoint we denote by Rn, and we denote this capital Hom to represent this right adjoint. So it kind of works as an internal Hom. And we call this Hom, capital Hom, as the rational Hom object, because this literally tells you that, so this capital Hom is a H module structure. In general, if you take the Hom, just the original Hom, then it need not be an H co-module. So that's why we have to consider the largest class in the original morphism class, which is an H, which has a H co-module structure, and that is the internal Hom. And we know this exists because of the right adjoint. And yes, so now we consider this. First of all, what we get, just like H invariance, we have H the co-invariance we can consider, and one can show that the morphisms in the category of this relative of modules is captured as the co-invariance of the Hom of Hom in the original category of D modules, in the internal Hom, but not the real Hom. It's the only subcategory of the original Hom space which has a H comodule structure. And this gives you, because of this composition, as you can see, composition by taking Hom and then by taking the co-invariance that we have, this would give you a way to compute the cohomology in the relative of category, and that's the third spectral sequence. And now to end the talk, I give a condition where this internal Hom is actually the real Hom of the category. That is, if you have, suppose your M is finitely generated as an object in the D module, then it happens that the original Hom in the category does have a H comodule structure. That means it has to be equal to the capital Hom that we defined, because capital Hom was the largest possible submodule with the H comodule structure in the original Hom. And in this case, we can see that the higher derived Hom functors for the relative of categories the modules over the relative of categories can be understood in terms of the standard X of the original D module and with the co-invariant functor. And yeah, so I think I will stop here.
Okay.
Yeah.
Are there any questions? Dennis, you can unmute yourself.
Okay, thanks for the talk. It was very good.
Sorry
so,
for that.
So I had a question about like how you would go about proving all of those spectral sequences. Do you just, I guess the main step, was it just showing that like your first functor sends injectives to the acyclics for the second functor?
Yes, that's like one of the most important part. That all these subcategories, like when you apply the functors, they preserve injectives.
I see.
Yes.
I had one other little thing I wanted to ask, if that's okay.
Sure.
So I wanted to ask, this big HOM, is it like hard to compute in general? Is that why we want comparison with the normal?